Okay, today we're going to be looking at 8.3 covalent bonding through 8.5, which gets into drawing Lewis structure, which is really a review of something you did last year. Now, in covalent bonds, remember you're sharing electrons. When you look at a sharing electron situation, there's really several different types of electrostatic interactions that occur. When you look at the picture over here, you've got two nucleuses coming together and they're sharing electrons in between. Well, you have repulsive forces between the two, as well between the two nucleus, as well as the repulsive forces that exist between the electrons involved in the bonding. And at the same time, you also have attractive forces between the nucleuses and the electrons. So you really have, once again, two competing force situations: the force of attraction versus the competing force of the repulsions between the other substances. Now, by sharing valence electrons, atoms and molecular compounds can achieve a noble gas electron configuration. So if individual atoms don't have a noble gas configuration, yesterday we looked at how metals and nonmetals can basically transfer electrons, forming a noble gas configuration in ionic bonding. Well, you can also do the same thing by sharing electrons. Two hydrogen atoms have the exact same strength of attraction to the electron, so really one's not strong enough to steal the electron from the other. So what they do is they come together and they share those two electrons. And when they share the electrons, both of them have a noble gas configuration like helium. Same thing happens here with the hydrogen and the chlorine. If the hydrogen comes in with its one electron and shares that electron with one of the electrons from chlorine, chlorine has a noble gas configuration like argon, 8 electrons, and hydrogen has a noble gas configuration like helium, 2 electrons. And you end up once again with a stable molecule. So when you're drawing Lewis structures for molecular substances, you really have to look at how you share the electron so that everything achieves a stable electron noble gas configuration. Now, one thing, and we looked at this yesterday, but I want to remind you again because it really has bearing on what we're looking at here with Lewis structures. For nonmetals, remember the valence electrons in a neutral atom is the same as the group number. So something like nitrogen, which is in group 5A, it's going to have 5 valence electrons, which means it's going to form 3 bonds to end up sharing and getting its 8. So when each hydrogen comes in with its 1 dot, the nitrogen, which remember has a total of 5 electrons, can share at each of those locations with the hydrogen. And now nitrogen has a total of 8 electrons. Each hydrogen has 2. Everything has a noble gas configuration. And you end up with the molecular substance NH3 ammonia. Now, when you look at something like methane, CH4, well, carbon is in group 4A. And group 4A has 4 valence electrons, so that means it's going to form 4 bonds. So methane, the simplest hydrocarbon, methane, ends up with 4 hydrogens, each sharing their single electron with the 4 dots from carbon. Everything, once again, ends up with a stable electron configuration. Last example I want to look at here is the world's most common substance, water. Remember, oxygen, which is in group 6A, has 6 dots. So it will share with the hydrogens in 1 spot each to make a total of 8 for the oxygen and 2 for each hydrogen, and you end up with a molecular formula of H2O. So when you're drawing Lewis dot structures of molecular substances, you're really looking at the sharing of those electrons so that everything ends up with a full octet. Now, some terminology that you need to understand with what we're going to talk about with these different structures. First of all, single covalent bonds. In the case of diatomic chlorine, each chlorine comes in with its 7. If they share 1 electron each, now they both have a full valence. So what you end up with is a single covalent bond forming between the 2 atoms at this spot right here. So that's an example of a shared pair of electrons. Now you can also see around each chlorine atom you've got unshared pairs like this one right here. So each chlorine atom really has 3 unshared pairs and then the 1 shared pair in between. Now you may remember from last year, it starts to get pretty confusing when you see these dots all over the place. So one of the things we typically do with our shared pairs is we draw them as a line. 1, it makes it a little bit easier to see with fewer dots around, and 2, it makes more of a connection between the two. So we usually draw our shared pairs as a line in between the two. So remember, every line represents a covalent bond. Every line then represents a shared pair of electrons. Now, if we can have single covalent bonds, it should make sense that we also have double and triple covalent bond situations. Now, last year, you never really got into what forms multiple bonds, but the things to watch out for would be carbon, nitrogen, oxygen, and then sometimes even sulfur. Those are the four culprits with multiple bonding. So if you see you have those, watch out for possible multiple bonding situations. And if you have multiple bonds, it's going to be forming between the carbons and the nitrogen and the oxygens and sometimes the sulfur. Now a double covalent bond is when you're sharing two pairs of electrons to reach your full octet. And that would be something like diatomic oxygen. 20% of what you're breathing in right now is O2 gas. The reason we write it as O2 and the reason it ends up with a double covalent bond, remember each oxygen comes with its 6 dots. If they share one, they each only have 7. So they have to share 2 times to get their full octet. So oxygen is actually diatomic, and its formula is O2, and it has 2 shared pairs and 2 unshared pairs around each oxygen. Now a triple covalent bond would be like the situation with the rest of what you're breathing in. Nitrogen gas, about 80% of what's in air is nitrogen gas. Well, nitrogen comes in with 5 dots each. So if they share once, they've got 6. If they share twice, they've got 7. So to get 8, they have to share a total of 3 times. So around each nitrogen atom, you have 1 shared unshared pairs, and you have 3 shared pairs existing between the two. Now, section 8.4 gets into the concept of bond polarity and electronegativity, both of which you should remember from last year. So really what I'm going to talk about here is reinforcing ideas from last year. Now, though atoms often form compounds by sharing electrons, that doesn't mean they always share equally. And that's what's happening between our two molecules here. One is diatomic fluorine, and the other is another type of 2-atom molecule, but this would be HF. Now, in the case of fluorine, both of these are fluorine atoms, which means they both have the exact same attraction to electrons. So what happens is neither one is strong enough to steal, so they end up sharing, and it ends up a true equal sharing. And the color that you see represented here, this lime green, green is basically an equal sharing type situation. So when you look at the HF situation, in this middle region here, you have some equal sharing occurring. But what happens in the case of hydrogen fluoride is the fluorine pulls much harder on the electrons, much higher in electronegativity, and it pulls much harder on those electrons than the hydrogen atom does, which means the electrons are more often on this side of the bond than on that side. And that means this side of the bond becomes slightly negative. Slightly is always shown with the Greek symbol sigma, so sigma negative would represent the slightly negative region of this bond or molecule, and over here it's shown in blue. And that would be where you have the electron deficit area. So on the fluorine end of the molecule, you have a much higher electron density. It becomes slightly negative. On the hydrogen end, you have a lower electron density, and it becomes slightly positive. And that's going to affect how this molecule interacts with other molecules around it. Now, a couple of terminology ideas related to bond polarity. Non-polar covalent is really what we call a true equal sharing of electrons. So in the case of 2 hydrogen atoms coming together, you have an equal electron density distributed throughout. That would be a non-polar covalent situation. In the case of our HF, you can clearly see that the electrons are shifted over towards our fluorine. That would be an unequal sharing of electrons. They're still sharing, but it's definitely an unequal sharing situation. Now, the next thing that's talked about in this section is electronegativity. If you recall from last year, electronegativity is the ability of atoms in a molecule to attract electrons to themselves. And you can see some general trends that exist on the periodic table in electronegativity. Now, if electronegativity is how strongly you attract electrons, when you're looking at a period trend, you can see that as you go right across a period, in general you see an increase in electronegativity, and that's because of increasing effective nuclear strength. Remember, every single period trend is caused by increasing effective nuclear strength, and as you go across, the nucleus is getting effectively stronger, so it's holding and attracting those electrons even stronger. Now when you go down a group, and the way it's phrased here is when you're going from the bottom up, it would be increasing. That matches the words that are up here. So basically when you're going in this direction, you would have an increase in electronegativity. And written from that point of view, that should really be a less than n. So from the bottom to the top, you have a decrease in your n value, which means you have a smaller and smaller and smaller atom. Remember, distance kills attractive forces. So by Coulomb's law, shorter distances mean stronger attractive forces. So as you go from the bottom to the top, you're increasing electronegativity. So as you're going down a group, yes, you would have a decrease in electronegativity, and that's because you have a greater N as you go down. Distance kills attractive forces. As N is increasing, you get farther from the nucleus. And it doesn't really matter what's happening with effective nuclear strength at that point. The greater distance is killing any attractive forces you have. Now, electronegativity and bond polarity, when you put the two ideas together and when you're looking at an actual bond, when you compare the difference in electronegativity, so that's really what we're looking at here. The key idea is difference in electronegativity. You can see the strength of the difference in the attractions between those two substances. If they're relatively close in electronegativity, you end up with a relatively small difference in electronegativity, and you end up with what's called a nonpolar covalent bond, an equal sharing of electrons. Well, when you go to greater than 0.4 up to 2.0, we still say they're sharing. They're still close enough in electronegativity. One thing hasn't stolen the electrons, but they're certainly not sharing equally, and you end up with a polar covalent situation. And remember, the closer you get to this 2.0 value, the less equal the sharing is going to be. And eventually we have to say, at some point, it's so unequal that we're not even sharing anymore. And the idea is, when you get greater than 2.0, so greater than or equal to, basically in that 2.1 range, it's so unequal we basically say it's an ionic situation. And what we're really doing here is trying to make black and white what's actually various shades of gray. Relatively low electronegativity difference would be nonpolar covalent. A larger difference, but still sharing, would be polar covalent. And then eventually, at some point, we have to say you're not sharing equally, and that's our ionic situation. Now, one thing you should understand about polar covalent bonds is the difference in electronegativity, basically in a nice, simple two-atom situation, ends up determining how polar the bond is going to be. In the case of HF, remember, fluorine is at the top of the halogens. It's the highest in electronegativity. So the difference between fluorine and hydrogen is very, very great. And you end up with a very unequal sharing. And you end up with a difference of 1.9 in the HF situation. And you can see it is very negative on this side and very positive on that side. A very, very polar situation here in HF. And therefore, it's a very polar molecule. When you look at something like HCl, it's still a polar molecule. You can still see the red and the blue on the two sides of HCl, but it's definitely not as polar as what was happening in the case of HF. And then as you go to HBr and HI, now your electronegativities are going down and down until eventually they're very, very close to what hydrogen is, and you can see the difference drop significantly. So when you get over here to something like HI, it's relatively equal in terms of its sharing, and therefore it's a nonpolar covalent situation. The other three would all be polar covalent, with HF at the top being the most polar covalent. Now, since we only have two atoms here in the tug of war, it should make sense that our actual bond lengths are going to be affected by this as well. You'll notice as the electronegative difference is increasing when we go up here, the bond length is decreasing, which makes sense. If HF is holding on to the electrons significantly stronger than HCl and HBr and HBI, it should actually end up closer together in overall bond length. So in this particular case, bond length is really related to our electronegative difference as well. Now that brings us to section 8.5, the last thing we're going to look at today. And really all I'm going to do here is remind you of the process of drawing Lewis structures for different molecules. Now remember, a Lewis structure is a representation of molecules showing all the electrons, those involved in bonding and those involved in not involved in bonding. So our shared and unshared pairs. So we're really looking at all the valence electrons, the ones involved in bonding and not involved in bonding. Now when you have something like PCl3, and you want to draw its Lewis dot structure, the very first thing you need to do is add up the total number of electrons in PCl3. So in the case of phosphorus, it's in group 5a, so it's got 5 electrons. In the case of our chlorine, chlorine has 7 electrons, group 7a, and there's 3 of them. 21 and 5 gives us total of 26 electrons to play around with here. So the very first thing you need to do is establish how many valence electrons you have available. Now, if it's a neutral atom, really at that point you're done. You just find the sum of the valence electrons. But when you have an anion or when you have a cation, you have to take into account that cations and anions have changed the number of electrons. Remember, when it's an anion, that means you've gained electrons. So that means you're going to add 1 electron for each negative charge. Now, when you get to a cation, you have to remember cations have lost electrons to become stable. So there you're going to subtract 1 electron for each positive charge. So when you're doing ammonium, which is NH4+, you would basically subtract 1 electron away from your total valence level because of that positive 1 charge. So that's your first step, is find out how many electrons you have available. And remember, if it's polyatomic ion, you have to take into account charge as well. Step 2 is to basically rough out drawing the molecule. If you remember from last year, we put in the central atom, space out the outside atoms around it, and connect them with single bonds. Well, what goes in the middle? Now, one thing we didn't really talk about last year was the fact that really the least electronegative element is the one that's going to go in the middle, not hydrogen, because remember, hydrogen can only form single bonds. Everything else is going to go around the outside. And you basically connect them all to that central atom with single bonds because they have to be bonded to the central atom. Now, having said that it's the least electronegative element, you normally don't need to look it up, because usually the formula, it's kind of obvious what goes in the middle. PCl3, phosphorus has got to go in the middle. CH4, carbon's got to go in the middle. The one you only have one of is going to go in the middle. The only thing you really have to watch out for is some simple organic substances, something like C2H6. The carbons would both basically go in the middle, and the hydrogens would end up spaced around them. Now, when you draw in your single bonds, before you move on, you need to keep track of where your electron totals are at. Remember, before we had 26 electrons available. That was our total number of valence electrons. Well, if we connect the 3 chlorines by single bond to the phosphorus, we've accounted for 6 of those 26 electrons. So at this point, we basically have 20 electrons left to account for. And that basically brings us to step 3. In step 3, you're going to give all of the exterior atoms, your outside atoms, full octets. And once again, you're going to keep track of your electrons to see how many you've got. In the case of PCl3, each chlorine really needs 6 dots to form its full octet, because remember, a bond is actually 2 electrons. So you basically have to draw in 6 dots around each chlorine. That's going to be a total of 18 electrons. So we were at 20 after last step. We just accounted for 18 more. That means we only have 2 electrons left to account for. So step 3 is to give all of your outside atoms a full octet, and once again, keep track of your electrons. So take stock of where your electrons are at. Step 4, give an octet to your central atom. Now in this case, phosphorus had 3 single bonds, that's 6 electrons. It only needs 2 more dots, so we're going to draw a pair right there. And that brings us to a total of 0 electrons. That would be what phosphorus trichloride would look like. And at this point, we're done. Now in some situations, you're either going to not have enough electrons to give your central atom a full octet, or you're actually going to have too many electrons. So there's really 2 other situations left to look at here. Step 5, which is only going to happen if you run out of electrons before your atom gets a full octet, would look something like this. At this point in the drawing of HCN, we would have connected our nitrogen and our hydrogen to our carbon, our least electronegative substance, by single bonds. The hydrogen has its full octet. We drew in 6 dots around the nitrogen to give it its full octet, but at that point we were done. We didn't have any electrons left to put around the carbon. So what you end up doing in this case is you multiple bond. So these 2 pairs of electrons can move to this region and form 2 single bonds. And what we end up with then is these electrons end up involved in bonding, and we end up with a triple covalent bond between the carbon atom. So when you form multiple bonds, you're pulling electrons from the outside into the inside and sharing multiple times. In the case of HCN, hydrogen cyanide, what we end up with is this structure then. Everything now has a full octet. So if you run out of electrons, you're going to multiple bond. And remember, carbon, nitrogen, oxygen, and sulfur are typically where your multiple bonds form. Now the last situation you may run into is if you have too many electrons. In other words, my fluorines each have 8 by putting 6 dots around them. My sulfur had 4 single bonds, so it's got 8, but I had to put 2 more electrons somewhere. Well, you're always going to put extra pairs of electrons on the central atom. And what you end up with here is an expanded octet situation, which is something we'll be getting into more in the next couple of days. So your homework tonight is really looking at doing these types of Lewis dot structures, as well as looking at simple Lewis structures and understanding polarities within bonds. So that brings us to the end of this set of notes.